Welcome. In this video I talk about hash maps. Hash maps are built into the standard library of Rust and are a very versatile data structure in their own right. They are a template data structure with a key and a value type and are thus very similar to unordered maps in the standard template library. We start with an example of using a hash map. To begin with, we need to use something from the standard library. That's instead collections hash map, and we need to bring this into scope to get the template and all its definitions. Here's how you define a hash map. Here is the string type, the key type, and U64 is the value type. Here I use the constructor to create an empty hash map, and I make it mutable such that I can then insert pairs. Insert has move semantics as before, so I have to produce a string and an integer and I can insert into the map. I can print maps with a debugging notation like this here. So if I build and run this, I get an illustration of the hash map with keys XYZ and ABC. Similar to vectors, there's also a constructor called withCapacity, where we can tell the newly constructed map that it should reserve space for 3 entries in this example here. It behaves exactly the same, but it is more efficient if you insert later on stuff. So far, I have ignored the return type of insert. So let's first see what it is. The return type of insert is again an optional. Let's print it. Namely, it's an option U64. Imagine this is a value here. So the semantics of insert is the following. It looks up the key given here in this pair, and if it doesn't exist, it inserts the pair and returns none. If the key already exists and is found, then the old value is moved out into the option value here, and the value is updated. So if I just do this down here again with a different value, let's put a 14 here, then we will see the following if I run this. First of all, in the first insert, I get back none because the key did not yet exist. The second time I do an insert, I get back sum of 12 because 12 was the old value of ABC. However, the value in the map has been updated, so we see a 14 now here. So therefore, insert is not actually a pure insert, it's an insert or update. Now, of course, we need to know how to look up and delete elements. Let me explain that. Here we construct the very same map as before. Here I form a string for the key of a string which I know is a key in the map. Now, if I do a lookup with the get method, I have to give a reference to the key here. So the method takes a reference, and what does it return? It returns an option to a reference of the value type. So this option thing is an algebraic data type which can either contain none if the thing is not found, or it contains some and then something of this type here. So if we find the thing successfully in the map, we get a reference to the very value in the map. Likewise, if I remove, I get an option of the value type. That is, if the thing is not in the map, I get none. And if it's in the map, I get some of the thing, and the value is moved out of the map. So therefore, when I do the lookup here, I first expect that I see the element, then I expect that I remove it and get the value out. I expect then that one of the keys has vanished from the map, and if I look it up again, the same key, then I should get none. So let's run this. Indeed, here's the map with 2 keys. The first time I look up, I get sum of 12. This is, of course, here a reference to the value in the map. The second time I remove something, I get the value out because it was in the map. and afterwards the key ABC with its value is gone in the map. And if I look up again, I get none. I've now rewritten the same program, but with matching syntax. Because for algebraic data types like the option type, it's very useful to have the match syntax. Let's look at this here. Here we look a key up, note with a reference here. We look the key up and we get as type the option to the reference. Now I can use the match statement on X to match what version of the type I get here. So here this says if it's a sum of XX, then I want to do that. And if it's a none, I want to do that. So if it's none, I want to do not found. And note that this sum of XX matching here unwraps the option value and binds the variable XX, which I can use here, to the type in the option. So if I go here, I see that XX is of type reference to a U64, which I can then conveniently print. Likewise, in this other case here, I look up something which is not in the map, and this time I expect to see not found, and this bracket here is just not used. Let's see how this runs. Indeed, I've put found 12 here, and here I put not found. So this matching syntax is very, very useful for not only for map lookups, but always for algebraic data types, and we will see quite a lot more later in the videos. I want to conclude this video with something which you could call a literal syntax. In this way, with the HashMap from constructor, you can give a list of key value pairs, which is directly used to initialize a hash map. So it's not actually syntax of the language, rather it is this array here, which is an argument to this from method. So if I look up this method in the library, you see I have an array of certain values, length, and array of key value pairs, and that is used to initialize the hash map. So here I get the same map as before, just I don't have to make it mutable and I don't have to insert manually. In this video we have covered hash maps. Note that hash maps are very fast. However, they are not using the fastest possible hash function. They are using something called zip hash, which is good for certain against certain denial of service attacks, but it's not the fastest. If you need faster hashes, you can exchange that, but this is a different story for a different time. Thanks for watching. I hope you enjoyed it.